So, we will now for the next few lectures start discussing modeling and measurements, which are essential components of a course of any course on iron and steel making. As we have seen in primary and secondary steel making, that in reactors molten steel flows essentially, and be it a ladle, be it a tundish, be it a torpedo car, we have interactions among phases. By interaction among phases, I mean that we may be injecting gases. The gases can be reacting like oxygen in molten steel, or non-reacting argon in liquid steel. So, we have reacting system, we have multi-phase flows, we have non-isothermal system. There may be temperature gradient in a system, and the flow itself, as we will see shortly, is turbulent. So, a lot of complexities are there in steel making processes, apart from chemical reactions, which are of course an integral component of the steel making system that facilitates change in composition of molten steel. Now, if you want to study all these phenomena like flow of molten steel, inclusion flotation, or temperature distribution or heat flow, in that case direct observation is going to be not so easy, because you can imagine, I mean, those of you who have gone to really visit and seen a steel plant, you look at a ladle which is filled up of 300 tons of molten steel. I mean, how difficult it is to approach that ladle, immerse a sensor and then record something. So, it is going to be, suppose if you want to measure temperature, it is not so easy a job, and primarily because the environment is extremely rugged. I mean, molten steel is bubbling, it is at 1600, boiling, it is at 1600 degrees centigrade, and it is an extremely hazardous environment. So, therefore, direct observation in steel making system is extremely cumbersome. It cannot be done on a daily basis. Of course, the plants do it, they have their arrangements, but apart from that, when we are developing the process itself, on a sustained basis, elaborate measurements are not really possible. And one more problem also you might have come across, that we require sensors, for example, which can sustain the rugged environment for a long time. And this is a big problem in steel making research, that we do not have sustainable probes or sensors. For example, if I want to measure temperature, then I can dip it one time and then measure the temperature, and then after that I find that thermocouple is of no use, I have to bring in a fresh thermocouple. Similarly, if I have to put some sensor from the bottom, I find that the sensor's life is extremely small, particularly in vessels like oxygen steel making systems, because of the tremendous amount of heat which are liberated in the steel as a result of reaction of molten iron, carbon with oxygen, silicon with oxygen, and so on. So, direct measurements in steel making system is very, very difficult, and this is primarily because of large size of the reactors. I mean, if you have such a huge size of reactor and I want to map the temperature, then I have to put the probe at infinite number of locations, and then possibly I can map the temperature. So, it is not going to be easy. A hazardous environment is radiating heat, and of course, I do not see, visually it is all opaque. So, I do not really see what is really happening. If the argon bubble is injected, how the bubble is going to rise through the melt, I have no way to ascertain all these things. So, since direct observation in steel making reactors is not an easy task, it is often cumbersome, and that is why often we resort to modeling. Modeling is a proven branch of engineering now. Today, for example, the swimsuits which are being designed by Speedo, they are based on some modeling work. Design of automobiles, they are based on modeling. Prediction of weather, they are based on modeling. You just name a field and you will find modeling is now extensively used. For example, when you find out that what should be the load at which a bridge is going to be, bridge will be collapsing, we do not really construct a full-fledged bridge and then subject that much of load. We scale it down, construct a small little bridge in our laboratory, and then do the load testing, and this is also one sort of modeling. So, modeling is there in every walk of human life today. Without models, we really do not see what is, because models are going to eventually generate some numbers. That is the objective of the modeling. It helps to quantify the subject. So, without models, we really do not see the inside of the process, and also we see that without measurements the models are incomplete, because models give us number and measurements give us a chance to verify those numbers. So, models and measurements, they go together in every walk of human life, for example. Now, many breakthroughs have been done in steel making through modeling, and as we will advance in this topic towards the later part, I will show you, give you specific examples, and in that the developments which have taken place over the years, modeling has played extremely important role. And if you look at the history, possibly particularly with respect to steel making, modeling studies are about more than half a century old, and we are expecting that in the days to come, when we will have to design better environmentally friendly process, we have to reduce specific energy consumption, we have to devise new processes, and in those directions modeling is going to play an ever increasing role. So, no study of iron and steel making today is complete without some discussion on modeling, and of course, as I said, models and measurements are like companions, they go hand in hand. So, when you talk of modeling, you have to talk about measurements. Now, models basically means representing a process, and we can represent a process either by a mathematical equation or an expression, or by a physical setup itself, by changing the scale, the dimension, the fluid, etc., and so on. So, we can have physical modeling, and we can have mathematical modeling. Represent the process in a smaller scale, of course, most of the time. Physically represent the process in terms of a mathematical equation or expression. I will discuss both this one by one. Let us first talk about physical modeling. So, we have a system which is in place, let us say a ladle, full scale ladle. So, this may be the industrial system, and the industrial system I can say is a prototype or full scale system. And I want to replicate the industrial system, and I say, well, this is my physical model. And as it is clearly shown that the physical model is smaller than the actual industrial system. Now, this is called the scaling down. On the other hand, if I have a model ladle, suppose when I am developing a new process, that time the industrial reactor does not exist. So, I have carried out some observation in a reactor, and then I want to design the industrial system, and this movement in this direction is the opposite of scale down, and it is scaling up. As I have indicated in this figure, the industrial system is bigger, the model is smaller. So, I would say it is a reduced scale model of the actual industrial system. Note that I have used a physical replica. Okay. So, imagine a cylindrical vessel of a ladle in the industry, and in my laboratory I have constructed this big size a ladle, and that is what it is. And this model that I have constructed is a reduced scale model of the actual industrial system. One has an option to build a full scale model also, okay, but that is going to be more expensive because you will require more material, it will be more difficult to handle, and so on. So, when you talk of laboratory scale investigation, we basically talk of reduced scale models. Now, question is that we have a characteristic length. How do you fabricate this physical replica? We fabricate by converting the characteristic length of the system or mapping the characteristic length of the system in terms of a chosen geometrical scale factor. So, for example, I can say this ladle may be the diameter of the ladle, I can say, is d sub full scale. So, this is the diameter of the ladle, the suffix is always, and this is the height of the ladle, which I can say is L sub f s. These are known to me. I want to construct this ladle, and before I can start constructing this ladle, I have to, as a modeler, specify one parameter, which I say is the geometrical scale factor. So, this is a modeler chosen. Depending on my resources, I am going to choose this scale factor, and this scale factor basically in steel making literature is denoted by lambda, and the value of lambda is greater than 0, but typically less than equal to 1. The modeler has an option to choose this value. He will decide depending on his resources that whether lambda should be 0.3, 0.5, 0.7 or 1. Having chosen the value of lambda, now I can say that, well, my full scale model so for every point in the full scale system, there is a corresponding point in the model itself. Okay, it should look geometrically identical, and for this, if I know the scale factor, I will be immediately able to find out that what is this diameter, and I will be immediately able to find out that what is this height of the ladle in my model once the scale factor is chosen. So, I say two objects are going to be geometrically similar if for every distance or for every scale, length scale, there is a corresponding length scale in the system. By the word corresponding means there is a constant ratio, which in this case is equivalent to lambda. Now, we can construct a physical model by considering the shape of the ladle itself, and this, whatever I have discussed so far, comes under the category of geometrical similarity. There are various states of similarity, but this is what we have to first consider, that physical modeling concerns with construction of physical replica, and the physical replicas are going to be derived on the basis of geometrical similarity. But how we are going to operate the model ladle, for example, if there is an argon injection here, at what rate argon I am going to inject? If there is steel here, what kind of a liquid I am going to say? The geometrical similarity does not talk about it. There are other states of similarities which I am going to come. Now, physical modeling, going back to physical and mathematical modeling. So, I can say that, well, we can think of a picture like full scale system, then we get model, and as I mentioned to you that this is my scale down and this is my scale up. Then we have physical model, and we can have mathematical model. physical model that we have constructed can be a room temperature model or maybe a high temperature model also. We will see what these are: room temperature model, or it could be a high temperature model. For example, in room temperature model, I can operate this ladle made in the laboratory either with mercury, which is liquid at room temperature, or with water. Now, why I am saying mercury, why I am saying water, what are the basis for it, we are going to see in a minute. On the other hand, when you talk of high temperature model, we have various options. We can have a small little system filled up with molten steel. We can have a pilot scale system, which of course will have a lambda value maybe 0.5, 0.6 or 0.7 of the full scale reactor. Laboratory scale model may have a scale factor of 0.3, 0.2. So, we can have a laboratory scale system filled with molten steel. We can have a pilot scale system filled with molten steel, or alternatively we can have a laboratory scale small system filled with Wood's metal. So, these are all molten dealing with molten metal. So, therefore, we can group them under high temperature modeling, and on the other hand, as I said, room temperature model will comprise of mercury based model as well as water based model or water model. Now, water models or water based room temperature models are extremely popular in steel making. Why it is so will be clear to you, and this is when you have water as the bulk liquid simulating molten steel. If you have water here, then I will say that what we are doing is nothing but aqueous modeling or water modeling. And this is extremely popular in today's context. Most of the steel plants, progressive steel plants, have extensive water modeling facilities. Many of the new designs, for example, Tundish furnitures, Tundish turbo stop, Tundish dam, etc., are evolved on the basis of aqueous modeling or water modeling. Now, coming back to the essence of or the principles of physical modeling, whether we have room temperature or high temperature model does not matter. The basis of physical model come from the principles of physical model stems out from one is geometrical similarity. I have already mentioned a little bit. I am going to continue that discussion. Geometrical similarity is essential. Then we talk about mechanical similarities. And in mechanical similarity, we will see there are various subdivisions, and of the subdivisions, what is important to us is basically dynamic and kinematic similarity. Third is thermal similarity, and fourth is chemical similarity. Mechanical similarity, following geometrical similarity, we have mechanical similarity, which talks about the forces acting in the system. Thermal similarity, steel is every time, all the time in motion. Steel is subjected to various kinds of forces in the reactors. So, geometrical similarity and mechanical similarity will always be considered. Thermal similarity may or may not be considered depending on what we wish to study. For example, if I say that, well, molten steel in this system is, we can treat it to be basically isothermal in nature. So, I can say that, well, if you are talking about isothermal behavior of molten steel, we can very well, there is no scope for any thermal similarity studies, because there is no transport of heat involved in the process itself. Similarly, if you are talking about that, look, there is not much chemical reaction going on. Okay, I am studying inclusion flotation. In that case, of course, chemical similarity will not come into the picture. So, these are always encountered, and these are encountered in specific cases. And the way I have written 1, 2, 3, 4, the ordering is very important to note. Okay, you should not interchange the order, as it is going to be clear to you in a minute. Now, when you talk of geometrical similarity, I have talked about the similarity of the shapes, and I have tried to impress on you that, well, all the characteristic dimensions need to be scaled properly, but it is always not necessary to scale all the dimensions, because some dimensions may be redundant. For example, I can have a vessel and say that I want to study the rise of an inclusion in the vessel. So, rise behavior of an inclusion I wish to study in this particular system. Now, the rise velocity will depend, of course, on the inclusion material. The rise velocity will depend on the bulk density. Rise velocity will depend on the viscosity. It will depend how much time it is going to take, will also depend on the depth of the liquid in the system. The diameter of the vessel has really no role to play as far as the rise behavior of the inclusion is concerned. So, in order to carry out a laboratory scale simulation, rise of inclusion, for example, in ladle I want to simulate, in that case I may find out that this is the dimension or depth of the liquid in the system that needs to be scaled up or scaled down, but the diameter of the vessel is really a redundant parameter. So, in that case you may think that the model really looks little bit distorted, because I am talking about a ladle in actual scenario, but I am using at the same time a vessel where the L by D ratio is not same as the L by D ratio, because I know that it is not so important a dimension as far as the rising behavior of an inclusion is concerned, and in that context, therefore, we can work out with a distorted model. So, the model becomes now physically a little bit distorted, but that distortion does not have any consequence on the final outcome of the modeling studies. So, it is perfectly okay if our understanding is appropriate to work out at many instances with a distorted model and yet get meaningful results. Now, it is very easy to draw this kind of a cylindrical figure and say that, well, this represents a physical model of this particular system. Now, you imagine a tun dish, for example. The tun dish has refractories, and I wish to consider that tun dish. I want to do a water modeling. So, I may consider fabricate a tun dish with any material, and typically what we do is we fabricate tun dish with plexiglass, which is basically a plastic, and it is a see-through plastic, so that we can see really when you use water how the water flows within the tun dish and so on. Now, in the actual tun dish we have refractory linings, we have tun dish nozzles. Now, these nozzles, they undergo typical various kinds of different extent of hydrodynamic wear during the process. Also, we have refractory linings which are wearing out as a function of the number of the heats. So, I have started with a tun dish. In the first heat itself, it looks perfectly okay, but as the process goes on, the geometry of the nozzle changes, the lining shape changes, there may be some skull formation or there may be some solidification. So, the geometry of the tun dish, actual industrial tun dish or the ladle, may not be same all throughout the process. So, by taking an engineering drawing of the system and fabricating a model, actually may not be truly representing the industrial system itself. So, there may be some element of uncertainty, because of the very nature of the steel making process itself. So, that can introduce some observations, some differences in observations, some distortion, and here the insight of a modeler is of great value. The modeler must be experienced enough in order to conclude that, well, if from an idealized system I can obtain this kind of a result, what would be the implications in terms of the actual reactor, which is little bit old, which is little bit worn out, where the geometry is not what I have considered here. Okay. So, there can be some differences between the actual geometry and the geometry that we are using in the laboratory. We must understand, and the name will be clear to you, that when you talk of modeling, there are certain assumptions, there are certain idealizations, and we must be knowing that if the model is entirely accurate, entirely predictive, or the model is resting inherently on certain assumptions. So far as geometrical similarity is concerned, I would not like to make any further statement, rather than saying that we should make every effort to have as close a geometrical similarity as possible. If it is not forthcoming, in that case we must understand the limitation and then possibly try to draw inferences on the impact of the differences between the shape of the two reactor, industrial reactor and the model in terms of the results that we are deriving from the study. Now, coming to mechanical similarity, three subdivisions are possible here, and these three subdivisions are basically, one is called static similarity, dynamic similarity, and the third is called kinematic similarity. Geometrical similarity is the similarity of shapes and sizes. When we talk of mechanical similarity, we are talking about similarity of forces acting on the two systems. And what are those two systems? The model and the prototype system. Static similarity is not of much importance to steel making. Static similarities are of extreme importance. For example, in civil engineering, particularly in loads in buildings, loads on bridges, these are all static structures. So the various forces acting on the static structures, they fall or they are extensively used in civil engineering. In metallurgical engineering, per se, they are not so important except for one or two situations. For example, static similarity would be, we would require static similarity analysis in order to predict that what would be the force which will be acting on the wall of a steel making reactor, ladle, tundish, or a basic oxygen furnace. Similarly, if you have a ladle, holding ladle, and then we would like to pull that ladle and then find out that how much the free surface will oscillate as a result of this pulling. So we will apply, from rest we want to accelerate the vessel and then lift the entire mass of the, which is sitting on a cart or a train, there the forces necessary and its consequence on the meniscus oscillation, that can be addressed through static similarity. So static similarity, basically the forces on the structures, but we are not concerned about forces on the structures. We are concerned about forces acting on molten steel, which is moving molten steel, and it is this movement of the molten steel which causes heat transfer, mass transfer, chemical reaction, take products from one point to another point, bring reactants from one point to another point. So it is the motion of the liquid that we are concerned about, and this motion of the liquid within the vessel is as a result of application of various forces. So that's what is within dynamic similarity. And when you talk of dynamic similarity, therefore we are going to talk about the similarity of forces which are acting on molten metal and or molten steel and not on the furnace or the ladle. Kinematic similarity talks about the similarity of velocities. This talks about similarity of forces. This also talks about similarity of forces. This is on static structure. This is on moving liquid. And kinematic similarity, when you are talking about in dynamics, because we are talking about velocity similarity. So essentially, they are interrelated, dynamic similarity and kinematic similarity, as we will see later on. Now, two systems. So let us again draw that. We have a ladle model. So for the time being, let us see that we have molten steel here and how the molten steel is being agitated. So suppose we are putting in some argon here and there is movement in the Similarly, we have molten steel here, we are putting in some gas. So, we have not molten steel, let us say water, and there we have steel. So, let us accept for the time being we can use water. I am going to of course explain that to you in a minute. So, we inject water. So, if we can use for example air also. We cannot use possibly carbon dioxide, because carbon dioxide if you use, then carbon dioxide will dissolve in water. Okay. So, it is going to be a reacting system. This is an inert system, argon does not dissolve in water, steel. So, the air also if the water is assumed to be saturated, in that case it does not dissolve, nitrogen and oxygen not too much. Okay. So, we can assume that this constitutes an inert system. Now, this system and this system, or the flow of water in this, the flow is going to be the systems. When we talk of systems, it is the molten steel contained in the ladle is now the system. The systems are dynamically similar if at corresponding points. So, let us say understand this. This is the line of symmetry. This is the center point of the system. This is r is equal to 0 and z is equal to, if this is the coordinate system that is being used, this is the radius and this is the z. So, this point corresponds to, this is an index of r is equal to 0, it is at the axis of symmetry, and z is equal to mid bath depth position. So, I can also have here this location which is r is equal to 0 and z is equal to mid bath depth. So, this point and this point are corresponding points. So, for every point in the model, because I have scaled it geometrically by a single scale factor, so for every point in the model full scale, there exists a corresponding point in the model. So, this is full scale and this is model. At corresponding locations and at corresponding times, the ratio of the forces acting on the system must be identical. So, suppose if there are several forces, now common forces which acts on fluids are inertial forces, viscous forces, pressure forces, gravitational forces, surface tension forces, or I can say a variety of surface and body forces. So, these are the common types of forces. When I talk of surface forces, I can talk about surface tension forces. When I talk about body forces, for example, I can talk about something like an electromotive force which are acting in the system. Okay. So, there may be, depending on the system itself, there may be various kinds of, but these are always there. You talk of a fluid flow or moving fluid, moving liquid, you have inertial force, viscous force, pressure force, gravitational force, and many other types of forces which will depend on the system configuration itself. So, at corresponding locations and at corresponding time, the concept of corresponding time I am going to explain in a minute. So, at corresponding locations and at corresponding times, the ratio of the forces must also correspond. So, therefore, I would say the ratio of inertial to viscous force at this point must be equal to the ratio of the inertial to viscous force at this particular point. Should be, therefore, I would say the ratio of viscous to pressure forces at this particular point must be equal to the ratio of viscous to pressure forces here. The ratio of pressure to gravitational forces here must be equal to. So, any combination I can take and I can say all the ratios of the forces must boil down to a constant itself. So, that is the essence of the dynamic similarity, and I would therefore summarize that two systems are said to be dynamically similar if at corresponding points and at corresponding time the forces acting in the system also, forces acting on the points, on the 2 points also correspond. So, therefore, mathematically I would say, if I can represent this as inertial force, this as viscous force, this as pressure force, this as gravitational force. Let us not talk about the, if I can explain with 4 different forces, I will be able to explain with all other forces also. This is not meaningful at this particular stage. So, what I am saying is that the ratio of inertial to viscous forces in model must be equal to ratio of inertial to viscous force scale. And if this ratio comes out to be C sub f, we will say that inertial to gravitational force and I can write down many such ratios. I will show you the consequence of this, but the first point is, how do you know that what are the forces that are acting on the system? So, we can find out the forces acting on the system by physically examining the process, or alternatively, if we say that we know the governing equation that describes flow in the system, then by looking at the flow equation itself, I should be able to find out that what is the forces which are acting in the system. For example, let us take this pipe flow, with which we all know. So, let us consider the fully developed pipe flow problem. Okay. So, let us not make that constraint of, let us write down only the 1D equation. So, I would say that steady state. So, I would write down, if I write down this is the x component, then I would say that, well, rho ux ux inertial forces. There may be other components of the inertial forces also along the y direction, z direction, that is not there. Similar terms can be there on the left hand side also. Then we have the pressure gradient. Then we have, if this is y and this is x, and then we have mu. Similarly, other components of the diffusion term may also be there, and then we have rho g sub x. For a homogeneous fluid flowing through a pipe, this is the form of the equation written in a very simplified way. I have not written the corresponding transport along the y and the z direction. I have not written the corresponding transport along the y and the z direction for the sake of simplicity. If I look at this equation, so I know the pipe flow problem. I look at the equation and I find out that, well, this term is nothing but the inertial force, inertial term. This is the pressure term. Okay. This is the viscous diffusion term, and this is the gravitational term. So, I can immediately say that, look, the fluid which is flowing through the pipe is the result of 4 different kinds of forces: inertial forces, pressure forces, viscous forces, and the gravitational forces. So, therefore, I want to say that if the governing equation is known to us, governing equation of flow is known to us, in that case we should be able to immediately identify by looking at the equation that what are the kinds of forces, and then say that, well, dynamic similarity demands that the ratio of these forces are going to be identical at corresponding points and at corresponding times. If you say, sir, I do not know the equations that are applicable to the system, in that case we have to carry out an elaborate analysis, dimensional analysis, carry out some experiment, and then find out that which are the meaningful forces. And it is only when we know that what are the meaningful forces which are acting in the system, we can now proceed to develop the dynamic similarity criteria. Now, this ratio of the forces can be arranged also in a little bit different manner. For example, if I say inertial to gravitational forces, okay, then I can say that inertial to gravitational forces, this equation should have been actually written in terms of, I would say, this is the second step, the inertial forces in the model to inertial forces in the full scale. That is actually full scale is equal to viscous forces in the model to viscous forces in the full scale. So, this is from the definition of the dynamic similarity, which can also be cast into this particular form. I just take out inertial forces by viscous force in the model, and then I write inertial force by viscous force. So, by transposing these terms from here, I should be able to come at this particular point. So, this is the fundamental statement of the dynamic similarity, the ratio of the forces. These are the same forces, the ratio of the same forces at corresponding locations at corresponding times must be equal. So, therefore, I would say that, well, this is really going to be C sub f. So, let me make these small little corrections. Of course, it does not change the conclusion drawn, whatever. So, the fundamental statement of dynamic similarity is this, and from this I can derive this particular expression, and this you see that this is more convenient for us to deal, because what is the ratio of inertial to viscous forces? The ratio of inertial to viscous forces is nothing but the Reynolds number. The ratio of the inertial to gravitational forces is nothing but Froude number. So, therefore, we can see that the ratio of the corresponding forces can be manipulated in such a way as to yield some characteristic dimensionless groups, and in this particular case, when inertial, pressure, viscous and gravitational forces are only significant, okay, in that case we will see that there are three dimensionless, three groups which will going to follow, and two of the groups I have shown you, Reynolds number and Froude number, and we have the third group is actually the pressure force to inertial force ratio, and that pressure to inertial force ratio is nothing but Euler's number. So, we have four different kinds of forces. So, four different forces can be rearranged in terms of three different ratios: inertial to viscous, inertial to gravitational and inertial to pressure. And if you do that, the inertial to viscous is nothing but the Reynolds number at the top, inertial to gravitational is nothing but the Froude number, the second one, and inertial to the pressure force is nothing but the Euler's number. So, therefore, I can say also that this equation, which is written in a dimensional form, can also be written in a non-dimensional form, which is Euler's number, 1 over Euler's number as a function of Reynolds and the Froude number. This is a non-dimensional representation of the governing equation of flow, in which inertial, pressure, viscous and gravitational forces are only relevant. If you have, for example, say, sir, I have one more force, suppose surface tension forces, then what happens? I get one more number here, and that number is going to be the Weber number. So, I will have 1 over Euler's number, or Euler number as a function of Reynolds, Froude and Weber number, in which not only inertial, pressure, viscous and gravitational forces are relevant, but also the surface tension force is important. So, therefore, the essential condition for dynamic similarity, I can now summarize that, well, we require Reynolds model must be equal to Reynolds full scale, Froude model must be equal to Froude full scale. So, if you entail these two, in that case automatically the Euler's number is going to be equal. Of course, I am dealing with a situation in which the Weber number of surface tension force is not important. So, the situation in which inertial, gravitational, viscous and pressure forces are relevant, if I can maintain this equality between the model and the full scale, in that case Reynolds similarity as well as Froude similarity, in that case I can say that yes, two of the systems, the model level as well as the full scale system, they are going to be dynamically similar.